this video, we're going to talk about something called a rate law. The idea of a rate law is that it gives us a mathematical relationship that relates the concentration of a reaction to how fast that reaction happens. Because like we saw earlier when we were looking at some of the figures in the last video, is that at different concentrations, our reactions will go at different speeds. So a generic way to write this is that the rate of a reaction is equal to K. I'm trying to write a lowercase k, it's hard to tell with my handwriting, times A to the n power, where this K is something called a rate constant. Now, for a rate law, it can have either one or multiple reactants in the law. So this is an example of a rate law where only one concentration determines how fast a reaction goes. But you also have ones like this, like rate equals K times A to the N times B to the M power, maybe. Or you can use X and Y, whatever letters you like. Or you could have three. You could have K times A to the N times B to the M, L, M, N, O, L. And I'm not going to write an L because L will look like a 1. O looks like that. We're just going to put an X on this. I don't have a better letter. So, you could have multiple components potentially. What you'll notice is they're all raised to a power. So that power is the thing that determines what type of reaction order that you have. So the way we're going to define our rate laws is based on how the concentration impacts that rate. And we're going to do it specifically through this coefficient here, which, as I just said, is related to the order of the reaction. So we're going to group these into categories. So let's look at some examples, and this will give you an idea. So we're going to start with zero order. So this is when you have your rate is equal to K, and we're going to look at the single component version. You can do this with multiple components. You can talk about the order of each component and then them all together. But we're going to start by just talking one at a time. So we have Ka to the 0 power. That 0 means it's 0 order. Remember, anything to the 0 power means it goes to 1. So this is literally just K. So what happens in a 0 order reaction is the rate does not change when the concentration changes. So the rate does not change when the concentration changes. And that matches with what we just saw because there's no value. Like I could make a 1, 2, 3, 242 billion, but when I raise it to the 0 power, it doesn't change anything. A lot of times we'll first introduce them by talking about what would happen if you doubled the concentration. Here, the rate would remain constant. It's also important to note that rate overall is in units of molar per second. That means for 0 order reactions, K is going to be in molar per second, since it's the only thing in our rate constant. Now for other orders, K changes its units. So let's consider first order. So in first order, instead of being to the 0 power, we have the rate is equal K times A to the first, which you're literally just going to write as K times A. Now here what that means, if we double the concentration, we double the rate. So if we double the concentration, the rate will double. What this means in general is that the rate changes linearly with the concentration. So it's going to change at the same rate. Sorry, not linearly. That's not the word I meant to use. It's directly proportional. It's terminology that'll make a little more sense here. So it's going to be directly proportional. That means if we triple it, the rate's going to triple. If we multiply it times a third, we make it so there's less of it, the rate's going to be 1/3. The other comment is our unit for K then is just going to be per second, which you might also see written as S to the negative 1. That's because A is in units of molar. So if you multiply molar times inverse seconds, you get molar per second. So that's our first two orders. We can also have second order. So in second order, your rate is going to be equal to K times A squared. In this case, if we double A, the rate is going to quadruple. If we triple it, then it will go up by 9 times. In general, what you're doing is we're squaring the concentration. So since we're squaring it, any change we have, it's going to square the amount of change it is. So what that means is that the rate is directly proportional, this time not to the concentration, but to the square. So the rate is directly proportional to the square of the concentration. That also means if it goes down, we'll have to square that too. So if you take the concentration down by a half, I'm going to bring my camera back. I like being here. So if we take the concentration down by a half, then it's going to go down by 4 times. If you decrease the concentration by a third, it's going to go down 9 times. If you take it down by a fifth, it's going to go down 25 times. Or if you raise it times 5, it'll go up 25 times. So I'm just squaring how much I'm changing it by. And that's what's telling me how much is going to change. Now, so far we've talked about how to mention the order for any one reactant. Now, let me see if I've got another blank slide here. Yeah. So we can also talk about this for an overall rate law. Like let's say we had something like this. Rate equals K times nitrogen monoxide squared times O2. We can talk about it for each component. So this reaction is second order for just NO. It's first order for O2. It is third order overall. So we just add them together if there's multiples. Now, most of our reactions will be 0, 1, or second order. You can see other orders. And just for long-term knowledge, I'm not going to ask about these regularly, but technically you can have things like half order or something like that. But generally we're going to round to something like 0, first, or second. We might look at some that are third order, but 0, first, and second are by far the most common. This has to do with what causes rate order. So, for example, we're not likely to see a fourth order reaction because what that really represents is 4 different concentrations are relevant, and why that is because 4 different molecules are involved in the reaction. Well, reactions that require 4 molecules to find each other at the exact same time are not very likely to happen because it's just a really uncommon occurrence. So we're not likely to see those. Whereas a second order reaction is how likely it is for 2 molecules to find each other. That is much more likely. And so we actually see second order reactions. So that's a limiting factor. You're not going to see realistically a 14th order reaction because it requires something that's an event that's so uncommon that that reaction just wouldn't happen. Now, that doesn't mean you won't have reactions that might involve 4 or 5 molecules overall, but usually those reactions occur in multiple steps. So overall, yes, your reaction might have 5 reactants being involved, but if you look at the chemistry happening, it is probably broken down into sub-steps where any one step only involves 2 or 3 of the molecules at most. The reason that's relevant is one of those steps is going to be slower than the others. And that slow step is your rate limiting step. And that's what controls how fast it goes. So that's why we're not going to see things much above second order too often. We'll see some third, but not really high ones. Now we just looked at that. How does this look like a problem? All that stuff we just did in determining rate laws. Well, let's look at these 3 examples. So this is A, looking at the case of 0, and then let me add a first and second order, what it would look like. So 0 order, you change the concentration, the rate doesn't change. That's a really good hint for those. So if you look at a particular reactant and nothing changes with the rate when you change it, then it's probably 0 order for that. Well, for first order, if you compare, here we doubled. Well, this also doubled. That's just first order. I can also look at these 2. Hey, we doubled again. These also doubled. Now, it doesn't have to be exactly double, right? It could be tripled or quadrupled or something. So you'll see a lot of doubles because a lot of times we're designing these experiments to test this, so doubling something's an easy change to make. Now here, when we double, we multiply times 4. And again, this times 2, this times 4. You could also look that if you were to take these, you get times 4, and if you compare these, you get times 16. So that's what's going to happen in second order. So this is how we're going to figure out the rate order for a reaction. We're going to measure the rate at multiple concentrations and then see what happens and figure out based on those changes what our order is. So what does that look like? Well, it looks like this. So we did 4 experiments, and our reaction involves 2 reactants, NO2 and carbon monoxide. And what we need to do is we need to pick two experiments at a time where only one thing changes. So for example, if you tried to pick experiment 1 and experiment 3, that doubles both the NO2 and this carbon monoxide. The problem there is you can't tell what change is caused by the NO2 and what change is caused by the carbon monoxide. So we're going to choose experiments where only one thing changes. By only changing one thing, that will let us limit what we're looking at to just that reactant. So for example here, I'm going to look at experiment 1 and 2. There, my NO2 doubles. My carbon monoxide doesn't change, so it doesn't impact this. Well, my rate went up times 4. That suggests that in my overall rate law, my NO2 is going to be squared because it's second order. Now, if I compare, let's say, 2 and 3, where the carbon monoxide changes but the NO2 doesn't, this stays the same. So if it stays the same, it's 0 order. I don't know why I wrote a T there. And that should be a Y. So when I do that, I don't even need to write CO, because CO to the 0 power just gives you 1. So this is the overall rate law for this reaction. This is the most common way of how you'll solve these. Please note, it doesn't have to be experiment 1 and 2 and 2 and 3 that you look at, right? Sometimes 1 and 2 might not be a good comparison, so you have to check. Also, some questions you can look, you'll have more than one option. For example, here we could have looked at experiment 1 and 4. There, we quadrupled the change in NO2. And if you're not sure, you can put it in your calculator, right? Like if I'm comparing, let's say I only had experiment 1 and 4. Well, I don't know the difference. So if I take 0.033 and divide it by 0.0021, I can see that raised it by 15.7 times, which is basically 16. So if I quadrupled the concentration and I increased the rate by 16 times, that's squaring it. So that would be second order, which is the same answer we get when we compare experiments 1 and 2. So choose 2 experiments at a time where only one reactant changes. Use those to figure out what the order of that reactant is. Repeat for all your reactants till you're done. Now, this is what it looks like when the way you design your experiment allows for nice, neat changes. But maybe, because of the way you're collecting your data, it's not neat and clean. Let's look at this example. So here we have 2NO2 reacts to form NO plus O2. We measured 3 concentrations and 3 rates, and I want to solve for the rate law. Now here, I can't just look at it. Like 1 to 0.7, I'm like, okay, that dropped by 30%. I don't know how to look at that one. So what we can do is we can start by writing a generic rate law. Rate equals K times, in this case, NO2 to the X power. Now, or N or whatever power you want it. What I'm going to do is I'm going to take 2 experiments where only NO2 changes. In this case, NO2s are only reactants. That's straightforward here. So we'll take these 2, for example. So what I do is I'm going to write out both rate laws, and then I'm going to divide them by each other because some of the information is going to cancel out. So first, I take rate. I'm going to number them experiment 1 and 2. So for experiment 1, the rate is 0.125 molar per second equals K, we don't know that, times 1.00 molar to the X power. Then our second one is 0.0613 molar per second equals K times 0.700 to the X power. Now I'm going to divide both of these by each other. What happens then is these K's cancel. If we'd had, like, let's say we had another component, like carbon monoxide, and let's say it was a constant, 0.100, 0.100. As long as it was the same number, it would also cancel. So as long as you're comparing two experiments where only one thing changes, this works. Now, I'll plug that value in on the left, and what I'll get is that 2.04 equals 1 to the x over 0.7 to the x. Now, I know 1 to the x power is 1. Or 1 to n, because 1 to any power I'm going to come up with is 1 times 1 a bunch of times is going to give you a 1. I'm going to solve it assuming I don't know that, because you're not always going to have a concentration that's exactly 1. So what to do here is, as long as both of our bases are raised to the same power, you can group them together. So what do I mean by this? This is the same thing as saying 2.04 equals 1 divided by 0.7 to the x. You can group them together. Now, our issue here is that we have our variable is now in our exponent, and we need to get it out of there. So we're going to use a logarithm to do that. Now, I'm going to take the natural log of both sides, because we tend to use a lot more natural logs in chemistry. If you take a standard base 10 log, that also works. So I'm going to take the natural log of 2.04, and if I do something to the left side, I have to do the same to the right. So I'm going to take the natural log of 1 over 0.7 to the x. In case you don't remember your rules of logarithms, the reason I did this is I can now move this out in front. The general form is, if I take the natural log of x to the y power, that's the same thing as I can move this out front and say that is y times ln x. And we can also move it the other way if that's useful for some reason. So you could have taken y times ln x and say that's ln x to the y. This is going to be a trick we use it's not really a trick, it's a math rule we're going to use multiple times to help us deal with when we have our variables and our exponents to get them out. So now, our x can be out in front. The other thing I'm going to do is so that gives me ln 2.04 equals x times the natural log of 1 over 0.7. I'm now going to divide by the natural log of 1 over 0.7 on both sides. Note, if you prefer, you can go ahead and do the natural log of 1 over 0.7. But I'm just keeping it in this form for now. And so now, that makes these cancel, and I'm left with x on the right. Now let's actually plug some numbers in and see what I get. So, well, I'm going to write out what my calculator says. 1.999 equals x. Well, that's really close to 2, so we're okay with saying x is 2. And when x is 2, that means we have second order. If we had gotten x was 1, it would be first order. If we got 0, it would be 0 order. If we got 0.5, it'd be half order, for example. So, okay, the problem actually asked for the rate law, so that means rate equals k times NO2 squared. So this is the version if you want to do it this way. Another thing we can do is the problem might have it where it wants you to solve for k. Well, then you can take any of your experiments and plug them in. So I can plug in 1 molar for concentration and square it, and I can plug in 0.125 as my initial rate and solve for k. In this case, we would get that k was 0.125 for this. And then unit-wise, it would be inverse molar times inverse second, since we need to end up with an overall rate of molar per second, and NO2 squared is molar squared. So we would need to multiply it by inverse molar times inverse seconds to get one of the molarities to cancel, and that would leave us with molar per second after we do that. Okay. So that's another way we can try to solve these rate laws. I'm actually going to show the last thing. I'm going to erase some of this on here. I just realized. So I said some stuff that may not. I'm going to show you what I was actually doing, just in case that wasn't clear. Because I want to leave some of the work on the screen, though, so I can reference it. This is one of the problems. A digital eraser is not a real board eraser. That's for sure. So let's show what in the world I was doing when I was talking through this. So What I was saying, in case we didn't notice, was that rate equals k times NO2 squared. And I'm going to purposely choose one of the other ones where it isn't just 1, because that can help. I'm going to choose experiment 2. You're fine to choose experiment 1 if you wish. So experiment 2 says 0.00613 molar per second is equal to k times 0.700 molar squared. So we take 0.7 and square it, and I've got 0.00613 molar per second equals k times 0.49 molar squared. So I'm going to divide both sides by 0.59 molar squared. So what you'll notice when I do this is that one of these molars is going to cancel with one of the molars squared, and we'll be left with that. And so we will get, let me put this in, and I will get 0.0125 m to the negative 1 s to the negative 1 equals k. So this is the way to solve for k, which would then let me write the rate law. I could take this number and plug it in to that k right there. Instead of writing k, I can actually write the number. So if you're asked to solve for k as part of solving for your rate law, or if it's a multiple choice question maybe, make sure you don't forget that step. Don't just leave it as k if you have enough information to be able to solve for it all the way if the question asks you to. So with that, that's the last part of sort of this rate law stuff. And what we'll do in our next video is we will start to explore what other types of information we can get by knowing the order of our reaction. There's a few other things we can do with it.